Good afternoon. So let's get started. So in the last class, we were looking at pack learning framework. Okay. So we were looking at what is called as probably approximately correct learning, right? And one of the key takeaways is that so we understand there are two issues here, right? So first thing is so pack learning framework was noiseless, right? So let me write here. So we looked at the noiseless framework, and the thing is, like you have two choices. Okay, so whenever you have a learning algorithm, you need to choose like what is the bag where you are searching from, right? So choice of bag or concept. So there we saw two issues. So one is um, bag should be large enough to capture C star, which we called as like true ground truth, or God-given classifier and so on, right? So we said that bag should be large enough to capture this, and even if we assume this, suppose this is assumed, okay, assumed to be true. The next issue is can we, when we learn from data, can we ensure that Cn reaches C star at some point, right? Can this be ensured? So this was the thing that we discussed there, okay, and we realized that there are examples where this doesn't happen, okay. So that is what we did in the last class, okay. So today we will be developing on this theme a little more, and we will be going towards what is called as Vapnik uh, Vapnik dimension, okay, VC dimension. I might have got the spelling wrong, but yeah. So this is called as a VC dimension. So we will be talking about this soon. So yeah, so this is where we are going. So before that, we have to define another model. So this model is again, it's called as empirical risk minimization framework. And here we will look at classification, noisy, and a classification problem. So this is what we are going to look at in this framework. So basically from noiseless we are moving to noisy, okay. So in noiseless itself we have understood that not all choices of concept bags are good, okay. So if you, for example, try to use a very complicated classification algorithm, it may not reach C star, okay. So that is what we learned. So now in the noisy case, what is it that we can say, okay. So this we are going to discuss now. All right, so let us try to formally fit the notations, all the notations that are required for this. So we have first what is called as the feature space, okay. Second, we have the output space. So this can be 0 1, or if you want -1 1. Basically it's a classification problem. Right now we are only interested in the classification problem. Third thing, p of x comma y defines the underlying problem space, right? Underlying pattern, if you want to say. So what is the meaning of this? So there is some distribution of x, and p of y given x also there is some distribution. Given that you have x, what is the chance that it comes from this y? The label will be this, right? So when we say something is noisy, what that means is like for a particular value of x, both y's are possible, right? So if you remember when we looked at so we looked at this base classifier where there were two different class conditional densities. Now, if you pick any point, let's say I pick a point here, right? So there is some chance that it comes from this distribution and there is some chance that it comes from this, right? Both these things are possible. So P of y given x is not degenerate. Is the point clear? I mean, do you understand what is the difference between degenerate and not degenerate? So for a particular value of x, there is some uncertainty around y. Okay, one thing before I forget, I need to start the attendance. Okay, so this is what we have, and the fourth thing is that we are given samples Sn, which is xi, yi, I equal to 1 to n. They are drawn IID from pxy. Okay, so we have been given samples like this. Now, point number 5, we can define what is called as a classifier. So classifier is a function h that goes from x to action space, right? So do you remember this? This is not something new. Action space can be equal to y. If that is the case, we are directly predicting the label. Okay, so this is a classifier. So don't get confused because there is a example like a could be y, and that means you are directly trying to predict the label. So this is what is called as a classifier. Okay, number 6, we have a loss function, right? So basically the classifiers themselves come from a hypothesis bag. So H is the collection of all classifiers. So that is a part of your learning algorithm. So your learning algorithm should also specify the collection of all the classifiers, and then there is of course learning algorithm here. Algorithm searches in H. Okay, so now we are going to talk about loss. Loss measures how good the classifier did on a particular point. So what does the loss say? So loss is a function from what action you took, what was the actual label, and what is the resulting loss, right? So this is what is a loss. So for example, 0, 1 loss, what is that? So L of h of x comma y. Okay, what is this equal to? This is equal to indicator h of x not equal to y. So this is your regular 0, 1 loss. Okay, so this is the loss. Now if you remember in the pack learning framework, what we had is there was a true God-given classifier. We said that all our patterns, I mean all the y's came from that C star. We had that in the pack learning framework. So here instead what we will say is that there is the best classifier in the bag, best in the bag. Okay, so that is h star is argmin h belonging to h, r of h. Okay, so r of h we know, r of h is expected value of L of h of x comma y. Okay, so r of h is actually also known as out of sample performance, or also called as true risk. So this is what we have. Ideally, what should the learning algorithm do?
Minimize this true risk.
Sorry?
The ideal learning algorithm should minimize the true risk.
Yeah, it should minimize your true risk, correct, or your out of sample performance. But unfortunately, we cannot even compute this, right? We don't even know how to compute this because the underlying distribution pxy is unknown, right? So this is unknown, right? So if this was known, what you would have done? If you
Just
actually knew,
minimize.
uh, how? If this was actually known, I mean, yeah, you can minimize that, but we have studied that when it is known, what we can do, right?
We have expected value of y given x as the best value.
Yeah, we can actually do for classification. We can do posterior, right? P of y given x we can compute, and then we can compute the base classifier. This minimizes the thing. For your regression problem, you can do expected value of y given x, right? So this is the optimal. If this was known, if known, then there is no machine learning to be done. We can directly do this. Do you all understand?
Yes, sir.
Okay. So that is the thing, but unfortunately we don't know the underlying pattern. So what we can only hope to do is we can do empirical risk minimization. So empirical risk, what is that? So this is defined as Rn hat of h. This is equal to 1 over n summation L of h of xi comma yi, and I'm evaluating on all the samples that are given to me. Okay, I try to compute this. This is called as the empirical risk, and my learning algorithm will do what is called as empirical risk minimization. So what it will try to do, it will try to return hn hat. Okay, hn hat, maybe I'll put a star also. Yeah, hn hat star, which is going to be arg min h belonging to h Rn hat of h. It can only do this. Okay, so this is what empirical risk minimization will do. What we wanted was h star. What we can only hope to do is hn hat star, which is for the given n samples, what is the minimum risk that I can get. This is also called as empirical risk, or also called as data error, or also called as in sample performance or error, right? Okay, so this is all the important things that you need to remember. Okay, so in the framework, I want you to understand each of these things. So let's see if everything is clear. You can just tell me.
Yes, sir.
Okay, so now if everything is clear, what should be the goal? What is it that we would like? If everything is going well, what is it that we should expect, right? See, one thing you have to understand, we are not saying that this bag, the best in the bag is the true thing. Okay, so remark. So H star, the best in the bag is not God given, okay, or it's not like true classifier thing, right? We don't know, but we are just settling with H star. Okay, for a particular bag, let me assume that this is the best, because there may be no such thing as the best, right? Because there is always noise associated with it. It may not be able, we may not be able to properly identify if something is best or not. So we are just saying, forget about what is the what is the best globally. Within the bag, suppose H star is given. Okay, so that is what we are saying. So it's not saying that H star is not equal to C star like we had before. Okay, so that is one thing you have to observe. Okay, so when given this empirical risk minimization framework, what could be a reasonable goal? Yeah, what should be our goal? So can someone tell me?
As n tends to infinity, like we should the hn hat star should like go to x star. We should
Yes,
get the best.
yes. So that is a reasonable goal. So what we would like to do is that as n tends to infinity, hn hat star, whatever we are learning from our algorithm should go towards h star. Okay, so this as n tends to infinity. Do everybody agree that this is a reasonable goal?
Yes.
Okay, so So some trivial example, suppose if I just choose H, which is having just one element, right? So H is a hypothesis bag with just one element. Uh, so then it's trivial, right? Because there is only one element. Whatever you can return is Hn star, just going to be the same thing as H star. So it immediately reaches, right? So goal is like when there are too many elements, right? So it may not happen. This itself may not happen. So that is what we are. If it doesn't happen, what is the meaning? I mean, suppose I cannot guarantee this. Then what do we do? Suppose as n tends to infinity, Hn star doesn't goes to H star. Then what can be done?
Or we should change our hypothesis back.
Yeah, we should change the bag. We should make it simpler, right? There are too many things that we have to search, so this cannot be done. So we have to throw away that bag. Okay. So anyway, so this is where we want to go. So this is a little bit whenever you are saying something goes to something, right? So we need to define in what sense. Okay. So those of you in the math program, you would have seen, right? So if you are saying something is converging to something, you have to tell what is the underlying sense in which it is going. So in that sense, what we will say is this. What we will say is what is called as consistency. So we require this goal, but we will define it in a more mathematical sense. Consistency of empirical risk minimization framework. So what we say is that for all epsilon and delta greater than 0, what we need is that if you look at the probability that Rn R of Hn hat star minus R of H star. Okay, if you look at this probability, if this is greater than epsilon, so you look at, so basically what you are saying for a particular n samples, right? So when samples change, my Hn hat changes, right? So let me make that clear. So let me write in a different color. So Hn hat star is a function of samples. So depending upon what sample I give, this will change. So therefore, R of Hn hat star also changes based on the sample that I'm choosing. Okay. So these both are random variables in samples. So samples are the thing that governs what this value is. R of H star is fixed. Okay, so when something is random, I can always ask questions like this. Okay, so what is this saying? This is saying that the deviation, I am having a deviation more than epsilon. I would like to be able to control this to be less than delta. Okay, so what is the catch? I mean, I would like to be able to control this, but some catch should be there, right? So the catch
as
is
the size of data set increases.
yes. So there exists, okay, there exists a n such that this is happening for all n greater than or equal to n that you have designed. Okay, so yeah, so if we are able to do this, then our goal is met. So this is our goal. Okay, so I think it was Advay who said this as the goal, but now this goal is actually formalizing whatever has been told. Are there any questions here? I mean, do you understand why this is a reasonable goal to have?
Yes, sir.
Okay.
Sir, so basically from yesterday's discussion and today's discussion here, we are just being told to get more and more data.
Yeah, from yesterday's discussion, we said that even if we have infinite data, it doesn't help. Yes, because in the concept, when you look at pack learning framework,
Right.
Yeah, even if we had infinite data, it didn't help. Okay. Yes.
Yes.
So now what we are saying, the yesterday's thing was an example with noiseless thing, right? We assumed that there was no noise in the pack learning framework. Now we are putting noise. So once you put noise, what happens is there is no such thing as the optimal classifier. It becomes, it is no longer easy to define it, right? So what we say is forget about optimal. Within your bag, whatever is the best, can you reach that?
Okay, sir.
So do you see the difference between what happened in the last class and now?
Yes.
Okay. So now working with a much simpler case so in the last class we saw even in the noiseless case, if you choose a large enough bag, it doesn't work. Now we are saying, okay, the last class discussion had the problem that you are assuming that there is a C star, which is not very realistic, right? So you don't hope that like there will be a perfect every x is very, it's not like a perfect clarity, there is always some noise involved. Okay, so given the house area, number of bedrooms, location, the price is not a fixed function, right? That is something that emerges as a result of discussions between the buyer and seller. There are many things that the learning algorithm does not see. So as a result, it is not realistic to assume a noiseless setup. So moving away from the noiseless setup, we are coming to a noisy case where we are saying forget about the global best. Can you tell us like which bags are there where you can reach from HN star to H star? If this basic goal cannot be met, you may as well not use that learning algorithm. Okay, so we are going to answer this question very systematically and give you a formula as to when this happens. So that is where we are heading towards, and the goal is what this is. So I hope this goal is clear at least, right? So okay, so now yeah, so this is what we have. Okay, so now I would like to just, this is where the goal, but before that we will just recollect some things from weak law of large numbers. Okay, so can somebody say what is a weak law of large numbers? At least informally, what do you remember? Sneha, can you tell what is weak law of large numbers?
Sir, it is the probability of the sample mean approaching the actual mean, like we did in the convergence of probability proof for the
Oh,
estimator.
yes. So yeah. So basically, what we are saying is you have Mn, which is 1 over n. Thanks, Sneha. So you have this xi, right? What we are saying is that for all epsilon delta greater than 0, probability that Mn minus true mean mu, okay, is greater than epsilon is less than delta for all n greater than n. So this is what weak law says. Now what we are going to do is we are going to apply weak law for our bag. Okay, so weak law of large numbers as applied to H, right? So pick a H belonging to H. Okay, fix H belonging to H. So now I will have Rn hat of H is equal to 1 over n summation L of H of xi comma yi I equal to 1 to n. Okay, this is my R of H. Now what was mu? Mu is equal to expected value of expected value of Mn, for example, right? So that was mu. So what is R of H? R of H is expected value of L of Hxi comma yi, right? So this is what is RH. So as applied to this hypothesis back, can someone tell me what is the thing? Sahil, can you tell me what is the weak law in this setup? So anybody else? Yeah, Siddhant.
Uh, Taking the definition of expectation is that's the application of the
Yeah, so
yeah.
if you take Rn hat instead of that Mn, you take Rn hat. So what we get is probability that Rn hat of H minus R of H, right, is greater than epsilon, is less than delta for all n greater than or equal to some n, right? So so what we are saying is that for all epsilon delta greater than 0, there exists an n. Is that okay, Siddhant? Is it what you
Yes.
were also saying? Yeah. Okay. So now this is the weak law. Okay. I hope everyone is able to understand this, because you have fixed an H. Once you fix an H, right, Rn hat is like Bernoulli. So are you able to appreciate this? Once H is fixed, Rn hat is Bernoulli. Why? Can someone tell me? Mahendra, are you there? Trisha, can you say why this is like this? Rn hat, why is it Bernoulli?
Yes, I just.
Yeah, can you tell? So basically, it is an indicator function.
It will take only 0 and 1 value.
Yeah, because it's a 0. Yeah, it's a 0-1 loss. So it's an indicator that h of x is not equal to y, right? So this is what is L of hx comma y is equal to this, right? So this is just can take either 0 or 1. So it's a Bernoulli. So it's like for the n samples that you are doing, it's like doing n coin tosses, and R of h is like your mu. Okay. All right. So I don't know if people are following this, but all right. So
It is clear, sir.
okay. So now this is what is guaranteed from weak law. So let us try to contrast between what is our goal and what the weak law gives. Okay, so there is a considerable difference, because in the weak law, okay, so can someone tell me the choice of n depends, what are all the factors governing the choice of n? So let me ask a question here. What governs choice of n? That is the question I would like to ask. So how do you change? What are all the parameters that affect n? So can you tell me? I'm putting how much ever you want, I will put. Okay. Sanjay, can you say? Okay, Rishabh says
Delta.
Epsilon.
Delta.
yeah, epsilon delta definitely. Yes, agreed. Anything else? Also the h, right? So see, I have fixed an h. This particular h may be a nice h, but there could be a bad h in my bag. So it also depends on h. Okay. So yeah, so this is essentially what controls this choice of n. So what we will say without proof now is that consistency of empirical risk minimization is achieved if and only if we have what is called as uniform convergence. So what does that mean? So let me try to explain that. So for all epsilon and delta greater than 0, what we need is that probability r n hat of h minus r of h is greater than epsilon is less than delta for all n greater than n. So how is this different from weak law of large numbers?
Here the mean is not fixed because of h.
No, h, no, r of h is like the mean, right? This is a known number.
Alright, yes. I don't see any difference by the way.
Yes, very good. That is what I do. There is no difference. So what we will do is we'll put a difference. So h belonging to h. Okay.
Sir,
So
we are using H instead of X star, right?
sorry.
We are using H instead of X star.
Here it is h. So if you see, there is no difference here and here. Without the soup, there is no difference.
Okay. Okay.
Okay. So now once we put soup, that becomes what is called as uniform convergence. Okay.
Then
So
what does SUP mean? Like,
so okay, yeah. So soup stands for supremum. Okay, so let me try to explain this. Okay, so this you would have seen if you, if you do optimization or if you have done math, you would have seen. But any case, it's not too difficult. So I will explain very quickly. Okay, so let's first try to talk about what is called as maximum. So let's say I give you a set like this. So what is the maximum here? 2, right? So now instead of giving a set like this, if I give you 0, 1, what is the maximum here?
1.
1.
1. So what about this? Next, I will give a open interval. What is the maximum here?
Not defined.
Yeah, this is not defined because maximum expects that I will give you an element from the set that is giving supplied to it. Okay, so maximum doesn't exist. So whereas supremum of 0, 1 is equal to 1. So basically this supremum you can think of is as the lowest upper bound. Is that all right?
Yes, sir.
Okay. So yeah. So we are saying that uniform convergence is achieved if and only if this happens. So few things that you can note here immediately. One is the choice of n. So choice of n only depends on epsilon and delta. Okay, so that is one important thing. So let's try to understand this quantity a little more. Okay, so in the context of uniform convergence, so let us spend some time trying to understand what exactly that expression means. Okay, so basically understanding uniform convergence. So let's see. So what we have is for all epsilon delta greater than 0, we have probability that supremum over h belonging to h r n of h minus r of h, this quantity is greater than epsilon is less than delta for all n greater than n. Okay, so now this is given to us. So whenever I am talking about probability, I should understand which is the randomness. So what is the source of randomness here? Yes. What is causing? Sorry. H is not random. It's just I'm going by one by one element.
H belongs to H where
H is not random, right? See, I'm looking at so there are different H. There is no distribution here. Supremum is not trying to put a distribution on H, right? Is that clear? Rishabh, if you can explain what you're saying, it will be useful. See, supremum, if assume that there were there is only one element in the bag, right? If there is only one element in the bag, there is only one edge, then supremum is just going to be, without this you can just throw away. Still there is a probability.
It's just because of the number of data points, right?
Yes. So depending upon what n I am taking, this is where the randomness comes, right? Because Rn of h depends upon what sample is given to us, right? So how does it perform for the particular sample that has been given? That defines Rn, right? So I may have, for example, if I am having let's say a learning algorithm, okay, so let me try to explain this. So suppose you have these 3 points, right, and this is your positive samples. Suppose these are the things, and you have a hyperplane like this. For this particular 6 points it is doing correctly, okay, but for any other 6 points, let's say I will take 6 other points. So what can happen is, there can be a few points like this also, right? The same line for this 6 points is doing completely wrong, right? So see, all these points it classified as positive examples. These points is going to classify as positive, whereas the actual thing is negative, because the true underlying thing might be something like this. Am I making sense? The true underlying may be like this, right? This is the true hyperplane. Because I evaluated and this was my h, so this is my h that I have chosen. For this h, right, for these 6 points it's doing perfectly. Rn h is 0, whereas for some other 6 points it is going to be 0, right? So here the error was 0, here the error will be 1. My god, people are not saying
Yes, sir,
anything.
it's clear.
Yeah. Okay, so this is what is the source of randomness. So what Sn gives, whatever, for different samples, this error can change. Okay, so this is where the randomness comes. Okay, so everything else is fixed. Rishabh had messaged. I don't know if this is clear.
Yes, sir, got it.
Okay.
Actually, I told same thing, means because we are choosing the n on the basis of n the RH or n of x.
Yeah. Okay. Fine. Okay. All right. So now, so you said n. Oh, in that sense. Okay. I thought you were saying. I think no. You were saying. All right. Okay. Good. So now, so now let us try to understand this even more. Okay. So my claim is, I want you to prove this in the here itself. This implies weak law. Can you prove this? If this uniform convergence happens, weak law is true. How do you prove it? So what do you need to show in weak law? We need to show that for all h belonging to my bag, I need to say that for all epsilon delta greater than 0, there exists an n such that, the same thing without the soup, right? Probability that Rn hat h, so there is a hat, okay, Rn hat h minus R of h is greater than epsilon is less than delta for all n greater than n. Okay, so this I need to be able to show given that uniform convergence is true. So how do you show it?
I guess we can take we can keep on taking the subsets of H
Mm-hmm.
such that these supremums are like different at each time, and using this, I guess we can like show.
See, I'm saying that supremum itself is I'm able to control, right? So if I fix any member, see if this is true, it's also true that any member will be greater, right? See, what I'm saying is this for the same epsilon and delta, this n itself works. So, so for a given epsilon and delta, you use uniform convergence and get an n. For this, using this n, you get this. Okay. Now I am saying that the supremum itself is controllable. Obviously, if I take any member of it, that also will be controllable, right?
Yes, sir. That's what I meant.
Okay. Okay. All right. So I think this should be clear. So, all right. So if you have any questions, please ask me now. So this is one aspect. Okay. So next, another aspect is I want you to understand how this thing works, right? So let's try to do some informal thought experiment, right? So let me try to do this. So let's suppose that you have all the samples. So it's a function of the samples. So given one sample, this may or may not be true, right? So I can have, let's say, Sn. Sn is one sample. I can think of another one, Sn prime, Sn tilde, and Sn double primes. So these are all the different samples when this happens. And whenever if there is so whenever I fix this sample, performance of every element in the bag is fixed, right? So let us suppose that this is the set of all the samples H1, H2 and H7. Let it be all the hypotheses which is making an error greater than epsilon. Okay, do you understand? So what is H1, H2, H5? This is basically this is all hypotheses where Rn hat H minus R of H is greater than epsilon. These are all the bad sets. Is that okay? So these are all the bad things. So when I say supremum greater than epsilon, this Sn will count towards the probability. So because this set is not empty, so when I look at whether see if these elements are bigger than epsilon, Sn will count towards this will count for my probability, count towards the probability, right? I don't know if you are understanding this, but see whenever I let me write again in some other color. So when I say P of A, what will I do? So I will look at all the outcomes omega belonging to A, and I will add P of omega. Do you remember this? So this is one way. Or if it is continuous, I will omega belonging to A, d f of omega, like that, like f of x dx, right? Do you remember this? F of x dx.
Yes, sir.
So x belongs to A. So that's what I'm saying. So whenever this set is non-empty, that will count towards the probability. Okay. So now for Sn prime, I may not get the same members. I may have H6 only. For Sn double prime, this may be empty. All the things in my bag are less than epsilon. The supremum is less than epsilon. So this can happen. And this can be H8. Right? So basically when I take supremum, it is not that there is one element in my bag which consistently is greater than epsilon. So supremum over this set is not a single hypothesis. Is that clear? So supremum, when I take supremum H belonging to H and I look at this Rn hat of H Sn minus R of H, right? When I try to do this greater than epsilon, when I look at this, I don't have one single hypothesis that is consistently violating the error. Okay, so it doesn't belong, it need not necessarily belong to my bag.
Yes, sir.
Okay, okay, fine. So I hope now people are able to understand the consistency. Let me just flash that again for your benefit. So what are we saying? We are saying this. We are saying that yeah, so if we want to get consistency of ERM, we should have uniform convergence. So that's essentially the conclusion of this. Okay, so this is two-way. So if you are having uniform convergence, then you will get consistency. If you have consistency, you will have uniform convergence. Okay, so how does that simplify, or what can we do now? So now that we have this result, suppose this is true. I have not given you a proof. I will give you a small one direction proof, but now what can we do? What is the use of whenever we give a characterization of a particular thing, what can we do with that? See, we wanted to look for a bag which satisfies consistency. Okay, so now I have given you a characterization. What can I do with the characterization? So I want to elect, let us say, a good MLA for my constituency. Okay, and what is good? I will tell if something is good if that person is not having criminal cases, is not having disproportionate property, and so on. Right? Telling what is good or not may not be easy. Whereas if I can check for uniform convergence, that is enough. Is that okay? Okay, all right. So yeah.
Sir, I didn't get the question.
So the question is, see, I have given you this characterization. Is this clear to you, Karthik? What is this characterization saying?
Yes, sir.
So this, do you agree that this is a reasonable goal to have?
Yes, sir.
So I am giving you a characterization of when that reasonable goal is achieved, right? So I may not be able to check for this. How do you even go about checking for this? You see, HN hat is I don't know how to check this, right? It may be much more difficult to check this, but it may be easy to check this. Okay. Do you see? I don't know, I have not shown you how to check for this, but suppose this is easy, then we just check for this. Whenever you are looking for a hypothesis bag, you ensure that it satisfies uniform convergence, then we are done.
Okay, sir. Okay.
Yeah. Okay, so all right, so this is what we will have to check for. So now what I will do, I will give you a proof in one of the directions. I will try to prove in this direction, and then that should help you understand why this is a good property to satisfy. Okay, so let us suppose that we have uniform convergence. So suppose H satisfies uniform convergence. So can we guarantee consistency of empirical risk minimization? So that is what we are going to prove. So let's do that. So again, let's try to see. So what you have is, we would like to control this, right? We would like to control how much this is deviating, right? So let's try to write control that Hn hat star minus R of H star. Okay, so I would like to control it. What I will do is I will control it by adding a few things. So R of Hn hat star minus Rn hat of Hn hat star. Okay, plus minus Rn hat of H star plus Rn hat of H star minus R of H star. Okay.
Yes, sir.
Yeah, so this is just telescoping. Okay, so because all these terms cancel out. All right, so now my claim is, what can you say about this? Is it, let me ask you, is this quantity greater than 0, equal to 0, less than or equal to 0? So you have three choices, A, B and C. So in the chat, can you say which of the three is true? So why don't I see responses from anybody else? Okay, let me pick somebody. Does somebody want to volunteer and explain why A is true, or shall I just pick someone?
Sir, H star.
Sir,
Yeah,
you go.
Karthik, please go ahead.
Okay. Uh, like in this term, the right hand side, uh, the risk on the right hand side is the like empirical risk of a true hypothesis, of our
Uh,
optimal hypothesis. So
right hand
it
side.
would be,
Okay.
yeah.
So
So
how was Hn hat star chosen? What is this equal to?
um
What is the definition? How did we choose Hn hat star? If you remember, we wrote it some time back, right?
Minimizes the
we chose it
empirical.
minimizing the empirical risk, right?
Okay. So what was that? So argmin H belonging to H, Rn hat star of H, right? Do you agree? This is what was Hn hat star.
Yes.
Yes. So if this is the case, do you want to revisit your answer?
Okay,
Yes, sir.
sir.
The empirical risk might be greater for the H star classifier, so it will be less than or equal to 0.
Yes, yes. Okay, so empirical risk. See, Karthik, do you understand? So this is the best you can do, right?
Like I
Kar-
meant, if we had the risk terms without the ends over here,
yeah, if you had
like
without the ends, yeah, that is true. If you had without the ends, that is true. All right. So okay, so this number actually is C. Okay, so I think the whole everybody has gotten it wrong, whoever answered, but I hope you understand that it is C. Okay. Okay.
Yes, sir.
Okay. So basically, what we have now is, see, all of these things, right? Whatever I am describing, it's. I mean, you can take away only the final result. I can give you as a capsule as to what is the ultimate result, but the very thought of how things are progressing, it also develops your ability to think, right? It's such a nice thing. Okay, so now anyway, so we have this. So now my claim is this is, I'm going to put a modulus here. With a plus here. Okay, is this correct? And if it is correct, why? See, again, I'm asking you things that are obvious if you think about it, but this needs some steps if you really have to be, mathematically correct. So can we do this? Can you always, so if I give you an expression such as a is less than or equal to b plus c, can I always say a is less than b plus c? That is what I'm asking you. This is not a question in machine learning, but in general about inequalities. Is this true?
I guess when all the ABCs are positive.
Okay, so is this positive first of all? Is
Yes,
this
sir.
possible?
Because,
Why?
wait,
Because
can you
the H star is the like
The minimizer.
opportunity minimizes. Yeah.
Yeah, so this is a positive number, okay? Because R of H star is the least true risk amongst all the things in the bag. In particular, this is also true. So this is positive. So as long as yeah, so once that is true, then we can actually take the modulus. So that way we get. So we can, from here we can get mod A is less than or equal to mod B plus C. Okay, so this is positive, then this also has to be positive, otherwise it cannot be less than or equal to. Okay, we don't have to prove this, but it has to be positive, right? Otherwise you will not have this itself in the first place. If this is positive and this
Yes.
cannot be not positive, right? So this cannot be the case. So from this we put this, and after this this is pretty easy. This is just a triangle inequality or something. Okay, all right. So so these things are now given. So now I will just leave this for you to do. It is available in my last year's lectures. If you want, you can see. But from here we can just prove. So here in this place we will use uniform convergence. Okay, uniform convergence will be used here. This is actually true by weak law of large numbers. Okay, so using the idea, so what is the idea? So you want to control control this for epsilon and delta. I would like to control it, but now through this right hand side I can use uniform convergence. I can say that this is less than or equal to 2 times the supremum of the difference. I can do that. Okay, and then I can control it. So that is the idea. I will leave you to finish the rest of the proof. Okay. So what we have shown is that if you are having uniform convergence, if this is true, we can get this, right? We can get consistency. The other direction is very non-trivial. We won't be able to prove it. So this is so far what we have done. So now tomorrow onwards, we will try to look at bags which satisfy uniform convergence. Okay, that's the goal for classes from tomorrow. All right, so I will stop here. If you have any questions, you can just stay back. Okay, so let me just stop the recording as well. All right, thanks.